Alrighty, everybody. The square root of negative 1. You've seen this since you were kids. We define this to be what?
I.
You cannot calculate this. It's defined. It's defined to be I. It's called an imaginary number. Okay? It exists only in your imagination, right? Well, not exactly. So I, by definition, is a square root. This is the definition. So what if I had something like this? Well, it is a square root, and I know the root of a product is the product of the roots. So would it be safe to say this? Would that be a correct mathematical statement?
Mm-hmm.
And that would be, therefore, 2i. That's not a definition. That's a calculation. I'm defining I this way, but now I can use it in a calculation. So I is called an imaginary number, and if I square I, what will I get? I'll get negative 1. Oh, okay. We know that any real number squared is going to be non-negative. But an imaginary number, when I square it, is automatically going to be negative. There are exactly the same number of imaginary numbers as there are real numbers. Because for every real number, I can just slap an I on it, now it's an imaginary number. So there's a one-to-one correspondence there. Okay? So if I have a purely imaginary number, I work like this. So now we're going to define what are called complex numbers, because that's really the bigger picture. Any number, we'll use the letter z. This is just out of convenience. We'll say z equals a plus bi, where a and b are real numbers. The script r is how we always indicate something's a real number. So a and b are elements from the set of real numbers. So a and b are real, so we define a plus bi to be a complex number. So for example, 3 plus 4i. 3 and 4 are real. 3 is a real number, 4 is an imaginary number. Every number is complex. Every number can be written in the form a plus bi. Now, a and b don't have to be integers, right? They could be fractions, they could be decimals, they could be irrational numbers. That's not important. So what we do is we say this is an element of, we use a script C. Script C is the big set. So we talked about this a while ago. I think I mentioned things like closure. The set of the counting numbers, 1, 2, 3, 4, 5, also called the natural numbers. If I throw in the 0, now they're called the whole numbers. If I do the positive and negative whole numbers, those are called the integers. If I consider every conceivable quotient of integers, those are called the rational numbers. We use a Q for quotient. If I think of the decimal form of a rational number, all rational numbers either have a terminating decimal or have an infinite repeating sequence. So, like 1/3 is 0.3 forever. Then the third possibility is an infinite non-repeating sequence. Pi, square root of 2, things like that. Those are called the irrational numbers. If I put the rationals and irrationals together, I get the real. And that was the king of the hill. Now it's just a, small sibling. Because for every real numbers, there is an imaginary number, and we usually you write them like that, IM. And when I put those two together, now I'm the king of the hill. Those are the complex numbers. The complex numbers is the king. We are mastering the calculus of real numbers in 2 dimensions this semester and next. Calc 3 is mastering the calculus of real numbers in 3 dimensions. How many here are engineering bound? One of your first upper division classes is a course called Complex Analysis, is where you master the calculus of complex numbers. And now the doors are opened up and now you see the grand picture and you say, oh, I didn't know we could do that. And a lot of the things that we've taken as absolute fact, turns out aren't absolute fact at all. There's no such thing as a no solution. That was never the right answer to any question. There might be no real solution. And for all practical purposes, there's no such thing as an actual prime polynomial. All polynomials can be factored. All polynomials have roots. But the roots are not always real. So when the roots are not real, we call it prime. But if we open it up to everything, we realize we take all the restrictions away at the same time. So this number here is a complex number. So the question, is a real number complex? My question, is the number 4 an element of the complex numbers? Well, can I write 4 in this form? Yeah. How?
0.
I've just written it as a complex number. Is an imaginary number complex? Is the number 3i a complex number? Well, can I write 3i as 0 plus 3i? So what we usually do, if it's a real number, there's no ambiguity whatsoever. If it's an imaginary number, there's no ambiguity. When we use the term complex number, all the reals are complex, all the imaginaries are complex, but when we use the word complex number, we're usually referring to something that has both pieces, just in general. Because if it was one or the other, we would just say real, we would just say imaginary, just so there's no confusion, okay? So far, so good? Now, give you some little pieces. So one of the big pictures. This is reality. This is the way things actually are, although you won't be using this for a little while. Really not until about 255. The students in that class will always ask me every semester, you mean we've been lied to our whole lives about math? And I'll say, no, you haven't been lied to. The truth has just been withheld. Like a great deal of the truth. Things that we hold too dearly are not always true. In fact, there's a significant amount of that we hold as absolute fact that is not even true in general. Because when it's something that's true for a real number is not necessarily true for a complex, so we actually have to establish rules that are always true for complex numbers. This is called the complex plane. This is actually the way things are. And what we do is we say, I'm going to take any point on the complex plane, and that point represents a complex number. The point on the complex plane represents the number a plus bi. Now think about it. My first coordinate will be the real, my second coordinate will be the imaginary. Therefore, if I consider every point on the complex plane, won't that literally match to every single complex number that exists? Because I can go infinite in every direction. You with me so far? That's an absolute across the board, no questions asked. Therefore, everything on this axis is of the form a comma 0, because it has 0 imaginary part. Everything on this axis is of the form 0 comma b, because it has no real part, and then everything else has both. Okay, that's the way numbers really are. So I'd like to find that distance. Now distance must be a real number. Pythagorean theorem, maybe? Can I use a little Pythagorean theorem here? You know, a and b are real numbers. So what's this going to be? Hypotenuse of a right triangle? Square root of a squared plus b squared. Now we need to give that a name. So remember I said before, we usually like calling complex numbers. We usually like just calling them z. Just it makes it easier. So I might have a z1, a z2, a z3 in the problem. No big deal. Now that sure looks like what?
Absolute value.
Sure looks like absolute value. How many remember in pre-calculus doing something like this? Anybody? They gave you a different word for it. They called it the modulus of z. You remember that term? And they said, no, it's not absolute value. It just looks like absolute value. And that is a lie from the pit of hell. No, this not only is absolute value, this is the definition of absolute value. The reason we use an absolute value symbol is because it is absolute value. The word modulus, I don't know why they use a different word, because that word actually means something completely different when you get to discrete math. No, this is absolute value. What is absolute value? It's the distance that something is from 0. Isn't that how you learned it as kids? So if you thought of a number line, it doesn't matter if a number is positive or negative. -5 and +5 are both 5 units from 0. So that's why the absolute value of 5 and the absolute value of -5 are 5. But that's on the number line, so that's on the real axis. What if I'm out here in space? Oh, then it's this distance. It's still absolute value. The absolute value of a complex number is how far it is from 0. And 0, this 0 is 0 plus 0i. It's still 0. Oh. Now, you guys know this. Right, calculus people, we deal with this occasionally. What is the square root of x squared? That's the absolute value of x. You guys know that. The higher level math people know that's the absolute value of x. And that's a really simple way to think of absolute value. It's the square root of the square. Well, if I've got no imaginary part here, then isn't this the square root of a squared? And I just said that's the absolute value of a. Same absolute value. It's the same thing. It's just now I'm allowing for the imaginary part to be part of the process. So if I'm dealing with a purely real number, the square root of something squared, that's the absolute value of that thing, because there was no imaginary part that I was adding to it. But in general, that's what it is. Wow. Okay, so let's hold that thought for a moment. Now I want to talk about the algebra, the simple algebra of complex numbers. Again, this is a reminder, okay? So Z1 will be A plus BI, Z2 will be C plus DI. How would I write this? Well, I can add the reals together. What would that be?
A plus C.
I have a BI plus a DI. Can I write that as B plus DI?
Yeah.
Remember, I is still a square root. So if I said 2 root 3 plus 5 root 3, don't you say that's 7 root 3? You just add the coefficients? So I just did the same thing. Is this still in the form of a complex number? Real plus imaginary? Yeah. That means the complex numbers are closed to addition. Remember closure? We talked about this a few weeks ago. Closure means if I combine any two elements of a set with whatever operation you want to talk about. If I combine those two elements with that operation, if my result is still in the set, then we say the set is closed to that operation. So if I add any two complex numbers, my result is going to be a complex number every time. Let me ask a simple question. If I take 3i and I multiply by 4i, if I take any two imaginary numbers and I multiply them, what will I get?
Negative 12.
I get negative 12, which is real. Are imaginary numbers closed to multiplication? In fact, you couldn't fail any worse. If you multiply any two imaginary numbers together, you get back a real. You never get back an imaginary number. Oh, so they're not closed. Question is, are complex numbers closed to multiplication? I would like to do Z1 times Z2. Z1 times Z2. Well, if these were binomials in baby algebra, you would just FOIL, right? Let's do the same thing. So what do I get? I get AC plus ADI plus BCI plus BDI squared.
Minus B.
So that's just minus BD, isn't it? So I got AC minus BD plus AD plus BC all times I, and that looks like real plus imaginary. We've just proved that complex numbers are closed to multiplication. They're closed to addition, they're closed to multiplication. Are irrational numbers closed to both addition and multiplication? If I add any two irrationals, will I always get back an irrational? If I multiply any two irrationals, will I always get back an irrational? So if I said, root 2 plus pi, yeah, I'm thinking that's still irrational. You agree? And if I said root 2 times pi, yeah, that's still irrational. So obviously irrational numbers are closed to addition, right? Oh, I just added two irrationals and got back a rational. I just multiplied two irrationals and got back a rational. Are irrationals closed to multiplication? No. All you have to have is one time it fails. Oh, the 0 is not irrational. 4, I'm pretty sure, is not irrational either. Ooh. So, complex numbers are powerful, complex numbers are special. So I want to go back to this guy over here. Okay, this one's kind of important. Okay? So there's a second way I can describe this. I put a theta right there.
Oh, good.
Now, forget that this is complex just for a moment. Think SOHCAHTOA for a moment. Okay? Lack of a better name, let's just for right now, I'm going to call that absolute value of z. That's that length, because that's what it is. Can you give me a SOHCAHTOA situation here? What's the cosine of theta? What's the sine of theta? Come on, be bold. A over magnitude or absolute value, if you will. And how about B over absolute value, okay? So that means that A equals absolute value of z cos theta, and it means that B equals absolute value of z sine theta. Am I right? So that means that every single complex number has an alternate way of being written. Can I factor out the absolute value of z? Now, cos theta comma sine theta I know is exactly 1 unit from 0. So this is an alternate way. This is generally referred to as the standard form of a complex number. This one has 2 names. It's called the trigonometric form or the polar form. It means the same thing. Now some of you, hopefully you did this in pre-calc a little bit. The polar form of a complex number turns out to be very, very useful, especially if theta is a common angle. So, draw a different picture now. And this is first day, first 10 minutes of the first class, if you remember. Except this is not the usual unit circle. This is the unit complex circle. So that means that this ordered pair represents the point. Now, there's something about the way I'm writing this that a lot of you may not have seen before, and it's neither right nor wrong, but it's a convenience thing. And I want to remind you of something. When I write cosine xy, there's a problem with that. Do you agree?
Yes.
Ambiguity. Is my argument xy or is my argument just x, or is the correct answer I can't tell because it's intentionally ambiguous? If my argument was xy, then I have to put parentheses. But if my argument is just x, then where should the y go?
In the front.
On the other side. It's sine theta times I. But when you're looking at that, you say, is my argument theta or is my argument possibly theta I? And you say, well, that would mean your angle's imaginary. You can't have imaginary angles. Actually, you can. You've been dealing with imaginary angles your whole life. In fact, of all the angles you've ever dealt with in your whole life, guess how many of them were imaginary? Exactly half of them. I'm going to show you in a minute. No, theta I makes perfect sense. Oh, I want it to be sine of theta times I. So traditionally, where do we usually put this I, as I may know? That's why a lot of you say, oh, I've seen cos theta plus I sine. How many have seen that before? The reason you put the I in front is just so there's no possibility of misinterpreting it. Because a complex number, you put the I at the end. But when you have a sine and cosine, unless you want to put parentheses around the cosine, nobody does that. People just put the I in front. That's all. That's the reason they do that. Okay? So, this is the unit complex circle. Okay? In pre-calc, you may have learned something called Gamov's theorem, which is really, really cool. It's really powerful. It's how you find the roots of numbers, whether they're real or complex. And I'll give you an example, because we're going to be using some of this today. Is this the same question? Square root of 1 is 1. What are the square roots of 1? The cube root of 1 is 1. What are the cube roots of 1? How many are there, by the way? 3 cube roots. 1, negative a half, plus or minus root 3 over 2I. You may or may not remember that. That one's in the second and the third quadrants. One of them is here, one of them is here, one of them is here. And if I cube them, each of them will give me back a 1. This is de Moivre's theorem. Some of you may or may not remember this. This is, of all the things you learned in pre-calc, it's considered a biggie, but you don't have any use for it at the time you learned it. You have nowhere to go with it. And that's one of the problems of some of the things we learn in pre-calc, that we don't know when and where we're ever going to use it, so we tend not to hang on to it, because you really aren't going to use it much for a while. But I can answer that question, which brings now probably the most famous and most important identity there is in all of mathematics. E to the I theta equals cos theta plus I sine theta. That value on my unit complex circle we just talked about, it's equal to E to the I theta. Now this is a formula that not only relates real and imaginary and complex numbers, circles, triangles, hyperbolic functions, all of these things are all related. Logarithms and exponential functions are going to show up in here also, are all related by this one identity. This identity is so huge and so important, a lot of people don't realize this. 2 professional sports franchises in North America were named after this person. This is how huge it is, because there's a lot of calculus people in the, in the sports world. Okay, there used to be a football team in Houston. They're now in Tennessee, and there's a hockey team in Edmonton. Wayne Gretzky used to play for. The Oilers. This is called Euler's formula or Euler's identity. Yeah, the Houston Oilers and the Edmonton Oilers were both named after this very, very, very famous mathematician. That's my story, and I'm sticking with it. This is Euler, not Euler. Yeah, Euler. Yeah, so in case you're wondering, wow. That's one of the reasons Wayne Gretzky was so great, because he was a mathematician first, and they recruited him out of the classroom and taught him hockey, but he was using stuff with complex numbers. Other players just couldn't keep up. It was incredible. I remember the early days. I mean, he'd do imaginary shots, and yeah, anyway. Euler's formula or Euler's identity is this, and we're going to derive a whole bunch of stuff using that. Now, what makes this so cool is if I had a complex number and I had to raise it to a power, that would be nasty. That would be actually very, very difficult. So I'm going to show you something that you may have done in pre-calc. Again, I don't care if you don't remember it, because you don't have any use for it at the time. So let's take a simple complex number. Let's take a simple complex number like, how about 2 plus 2i? I want to write this, first of all, in polar form. Because what I'd like to do is, I'd like just for the heck of it to do, I don't know, z to the 10th power. Do you want to multiply that out 10 times and keep track of the terms? I mean, I don't think you do. Plus all their different powers of I. This is what's so cool. Okay, so first of all, on my complex plane, I'm about right here, right? 2, 2. Won't my angle be pi over 4 or 45 degrees? Yeah. And won't this be 2 squared plus 2 squared or root 8? Mm-hmm. Root 8 is 2 root 2. So can I write z then as 2 root 2 times the cosine of pi over 4 plus I sine pi over 4? I've just now written it in polar form. Okay? Because that's root 2 over 2, that's root 2 over 2, and I get this back again. Well, how does this help me? Because now let's write it in Euler's form. Won't this be 2 root 2 e to the I pi over 4? What do you think? E to the I theta. So z to the 10th power is 2 root 2 e to the I pi over 4 to the 10th power. Well, what's 2 root 2 to the 10th power? I think that would be 32,768. I used to teach programming. That's 2 to the 15th. That's actually a common number. What do you do with exponents here? Multiply. What's 10 times pi over 4?
2.5.
So would that be 5 halves? 5 pi over 2? Pi, 2 pi, 5 pi over 2 would be right here. Agreed? What's the cosine of this? Notice 5 pi over 2 and pi over 2 are the same size. So the cosine would be 0 and the sine would be 1. I'll write it this way if it helps you, what we just did. Well, that's 0 and that's 1. So the answer to this question, c to the 10th power, is 32,768 pi. Which is a heck of a lot easier if I use Euler's formula than if I actually tried to multiply it out. Now, this works because we had a common angle. If it didn't have a common angle, it'd be a little bit uglier. But it's a very powerful use of this tool. I could raise that to any power and it would be a fairly simple thing, okay? That comes from something called de Moivre's theorem, the idea of the roots and move it around. Now, and we're going to come back to this in a moment. Now we are ready to define the hyperbolic functions. Okay? You have a key on your calculator that looks like this. It's an HYP, it says. Everybody locate that key on your calculator. See the HYP? That means hyperbolic. So press HYP and then press cosine, and it should say COSH on your screen. So you just told your calculator, I want the hyperbolic cosine. So this is hyperbolic cosine. This is defined to be the cosine of IX. Remember I said a moment ago, imaginary angles? Oh yes. We're going to be dealing with imaginary angles all the time. In fact, the rest of today, it's all about imaginary angles. It's crazy. So when you take the hyperbolic cosine, I would like you right now to take the cosine of 3i on your calculator, your cheap calculator that you have right in front of you. Can you take the hyperbolic cosine? So in other words, on your calculator, you're going to do this. Oh, by the way, you need to be in radian mode. Sorry. You have to be in radian mode or your answer won't make any sense. Make sure I'm in radian mode here. And what'd you get?
10.06.
You got approximately 10.06. You just took the cosine of an imaginary angle and you got back a real number. You realize that's what you just did. You took the cosine of an imaginary angle and you got a real number. But wait, doesn't sine and cosine only return numbers between what? -1 and 1. Well, yeah, that's if my angle is real. Oh, if I put no restrictions on my angle, then sine and cosine can actually return all real numbers. It's one of those lies that you've been told that, you know. But yeah, I'm only working with real numbers so far. Well, no, we're going to see that we're going to be working with other stuff. So the hyperbolic cosine will return everything outside the range of -1 to 1. You'll get all the rest of the whole number line. Whoa. Now, if that's not cool, I don't know what is. But okay. I'm just giving you a simple example. This is what the hyperbolic cosine is, okay? The hyperbolic sine, which we write this way, is defined to be -I times the sine of IX. So although the sine of IX may turn out something real, the -I in front of it means that guy's generally going to be imaginary. Yikes. Now, is there calculus here? Yeah. Remember, I is the square root of -1. So I technically is a constant, isn't it? It's an imaginary constant, but it is a constant. And constants obey all the rules of calculus. I would like to take the derivatives of the hyperbolic cosine of x and the hyperbolic sine of x. I would like to take both of these derivatives. Okay, well, let's see. I'm differentiating cosine of thing. So what should my answer be? Negative sine of thing. I is a coefficient. So what's the derivative of ix? Just I. I'm going to put it in front. Okay? Now I want to take the derivative of this. Well, isn't the derivative of the sine of thing, isn't that going to be cosine of thing? I had a negative I in front. And what's the derivative of ix, once again?
I.
It's I. So I'll just put it here. Wait a minute, what's the negative of I squared? Wouldn't that be a positive 1? I squared is negative 1, so the negative would be positive 1. You see something really cool here, folks? We have just proved the derivative of the hyperbolic cosine is the hyperbolic sine, and the derivative of the hyperbolic sine is the hyperbolic cosine. No pluses or minuses to worry about. Well, that's kind of cool, right? You know, I don't know what I'd do with that yet, but right off the bat. Now, there are other hyperbolic functions. We don't spend a lot of time on the other ones, okay? I'll just introduce you to them briefly. And again, I have the posted lecture notes. It gives great detail on all of these things. These are the two, though, we want to really concentrate on. So, how do I tell my calculator to do sines and cosines of an imaginary angle and such? That seems kind of impractical, doesn't it? Well, let's go back to Euler's formula for a moment. Okay? Let's let theta equal negative ix for a moment. Now, off to the side, I'm going to show you something because I need to do this because you may or may not remember. So, real quick review on something that you may or may not remember from a baby algebra class, and that's the concept of odd and even functions. How many have heard the term odd and even functions before? Yeah, this is low level stuff. This isn't calculus. So we say that f of x is even if f of negative x equals f of x. So from a graphic standpoint, that means whatever it looks like on the right, it's a mirror image on the left. It means you have symmetry about the y-axis. So give me any positive x-coordinate, negative x-coordinate, they produce the same y value. Why do we call it an even function? Well, if I said f of x equals x squared, x to the 4th, x to the 6th, any even exponent is going to have this. Are there any trig functions that are even? Yeah, there are two. Cosine and secant. Oh, so let's do a quick example. I have f of x equals 6x to the 4th minus 3x squared plus 5. I want to prove this is an even function. See, if I have one thing, but then I add a bunch of even functions, the whole thing's still an even function. What is f of negative x? Well, it'll be 6 times negative x raised to the 4th minus 3 times negative x squared plus 5, and that would be 6x to the 4th minus 3x squared plus 5, which is exactly the same as my original f of x. If all my exponents are even, including constant terms, cosine, right, secant, that's an even function. I have a cosine in here that I'm about to evaluate at a negative angle. I need to know that. What's an odd function? Anybody remember that one? It's very different from this. This one is very different. It has rotational symmetry. If I rotate my graph 180 degrees, it will look exactly the same. Well, what has that property? I don't know, x cubed, x to the 5th, any odd exponent. How about trig functions? All the rest of them. Sine, tangent, cosecant, cotangent are all odd functions. But that's actually really, really important. So let's do the same thing that we just did here. I want a simple illustration. Let's consider f of x is 5x cubed minus 6x. So what's f of negative x? Well, that'd be 5 times negative x quantity cubed, 6 times negative x. So this would be negative 5x cubed plus 6x, which is the negative of 5x cubed minus 6x, which is the negative of f of x. Okay, so an odd function, if I evaluate it at a negative value, it's the negative of the original function because of this type of symmetry. Okay, it's very useful, and we're going to use this later on in this course often to make problems potentially easier when it applies, obviously. So I want to do this on that statement right there. Yeah, it's got some play in it. So if I replace theta with negative ix, then this will become e to what? I times negative ix is what? I times negative I is 1. So this will become e to the x. And that equals cosine of negative ix plus I sine of negative ix. Wait a minute. E to the x, you can't get any more real than e to the x. I can describe e to the x as the sum of these two wicked imaginary kind of things. Oh yeah. Yeah, there's a lot of hidden secrets out there. Cosine is an even function. So isn't this the same as just cosine of ix? Because cosine is even. But we just said sine is odd. So what happens here? Is that important? It's astronomical. What do I've got there? That means that e to the x is equal to the hyperbolic cosine of x plus the hyperbolic sine of x. Oh my gosh. E to the x. We can't think of anything more real than that. It's equal to the sum of these two wicked, crazy, nasty things. Now, let's replace theta with positive ix, shall we? If I do this, and I replace theta with positive ix, then I'm going to have I squared x. And I squared is negative 1. So that would give me e to the negative x equals cosine of ix plus I sine of ix, which is the same as cosine of ix minus negative I sine ix. So that means that this is the hyperbolic cosine of x minus the hyperbolic sine of x. So e to the x is the sum, e to the negative x is the difference. Could I then define the hyperbolic sines and cosines in terms of e to the x's? Yeah. Yeah, I can put them together. So I'm going to write it right under here. We've just proved it. This is actually a pretty simple proof. Okay? If I add these two together, what will I get? Well, those will cancel, won't they? So if I add these two things together, let me see this for a moment. If I add those together, then e to the x plus e to the negative x will equal what? 2 hyperbolic cosine of x. Then hyperbolic cosine of x is simply half of e to the x plus e to the negative x. When you ask your calculator to do the cosine of 3i, did it actually do a 3i? No. It did this, because it's the same thing. In other words, when you're actually calculating a hyperbolic, you cannot calculate the sine or the cosine of an imaginary number. But if I convert this to the exponential version, now e to the x we think it was purely real. So if I have an imaginary angle, I have real e's. That's crazy. Now, go back to here. What if I take this and I subtract this? Then the cosines will cancel. And I would see that e to the x minus e to the negative x is 2 times the hyperbolic sine of x, which means this. Wow. That is crazy, isn't it? Hyperbolic sine, hyperbolic cosine. The definitions involve imaginary angles, but these are identities that are very, very practical. Now, if a math textbook today even has the hyperbolics, what's very sad is they will probably define them this way. This is not the definition, this is a result. And then people always ask me, well, why is it called a cosine or a sine if it's got e to the x's in it? Well, it's because I'm using Euler's identity. These are the definitions. There aren't versions. This is the truth. This is a result of the definition and this identity here. If I put them together, so from a calculation standpoint, this is way more practical. Now, if I said take the derivative of this, you're going to get this. If I said take the derivative of this, you're going to get this. Okay? So here's the nice thing. The derivatives of the hyperbolics, piece of cake. And it's actually quite simple. I would like to differentiate the hyperbolic cosine of, I don't know, x to the 4th power. Well, that's going to be the hyperbolic sine of x to the 4th power times 4x cubed. I'm done. The derivatives are just like anything else you do. It's simple things. I don't need to change that to the exponential version. I would only do that if I had to calculate, but your calculator's doing it for you anyway. That's it. Yeah, that's pretty clean. Now I'm going to define the hyperbolic tangent because the hyperbolic tangent is actually really important sometimes. The sine of theta over cosine of theta, we know that is tangent of theta. Agreed? So the hyperbolic tangent is the hyperbolic sine divided by the hyperbolic cosine. How convenient. And the derivative of the hyperbolic tangent is the square of the hyperbolic cosecant. And the hyperbolic, or secant, the hyperbolic secant is the reciprocal of the hyperbolic cosine. Those don't change. So the secant, cosecant, tangent, cotangent, all those relationships still remain the same in terms of hyperbolic cotangent is the reciprocal of hyperbolic tangent. You're never going to work with hyperbolic cotangent or hyperbolic cosecant. You're rarely going to work even with hyperbolic tangent. It's just that this is true. Now, the Pythagorean theorem becomes really interesting when I have hyperbolics. Think about this for a moment. We know that the cos squared of theta plus the sine squared of theta is always equal to 1. So does this apply to the hyperbolics? Well, here's the question. The hyperbolic sine has that there, doesn't it? So if I said the sine of ix, if I multiply both sides here by multiply both sides by I times negative I, we already said that's positive 1. So the sine of ix is I times the hyperbolic sine. We're going to do the hyperbolic Pythagorean theorem. And you would actually write it like this. How do I write this? I'm going to write it as, I'm going to do the ix first, okay? The hyperbolic, if I do ix, that's the hyperbolic cosine, okay? I have to do negative I times that for it to be the hyperbolic sine, but I just want to do this guy here, okay? So if I do this, this will equal 1. That will still equal 1. Okay? Because it's still theta. But if I put it in terms of the hyperbolics, this is now the square of the hyperbolic cosine, and I put the square here. Because the cosh is the function. You're not taking the cosine of hx. The h means hyperbolic cosine of x. But what did we just say this was? I'm squaring the I. So what does that mean? Minus 1. So the Pythagorean theorem for the hyperbolics is the hyperbolic cosine squared minus the hyperbolic sine squared is 1. Is that crazy or what? That's called the hyperbolic Pythagorean theorem. Now, I don't know if I've told you guys about this. I told one of my other classes. A few years ago, visiting Powell's bookstore in Portland, it's the biggest bookstore probably in the world. It's ginormous. The math section alone is probably 3 of these rooms. And I found a book called YE equals MC squared. Have I mentioned this to you guys? My Cal 3 people are very interested in this. It was written by 2 Cambridge physicists. And it says right at the beginning, you don't even need to have a math background to understand this book. That's not quite accurate, but they're using 4th dimensional non-Euclidean geometry and the hyperbolic Pythagorean theorem. See, the Pythagorean theorem we think of as the sum of the squares equals something. The hyperbolic Pythagorean theorem is the difference of squares equals something. And it's 4th dimensional geometry. Very interesting read, a little bit difficult. I learned, for example, if I run really, 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 really fast, I'm going to age slower than you guys. It's true. Mm-hmm. And it's actually a very, very simple proof. They used a pendulum clock. You're standing still and there's a pendulum clock on a train passing by going very fast. Time actually is moving slower on the train. You can actually prove it. The proof's not that complicated because they use a pendulum clock because it's really easy to measure things. So how fast you're moving has a lot of effect. They refer to the speed of light as just the universal speed limit. They never actually use the numbers. But the explanations they're a little bit difficult. So when they say you don't have to have a math background, I think you have to have a math background. It's a little bit heady, but it is really, really cool stuff. But my point is they're using this kind of stuff. Does anyone know what non-Euclidean geometry, what that means? The geometry you have studied all your life is called Euclidean geometry. Euclid was the most famous geometer. Non-Euclidean, simple explanation. Okay, first of all, yeah, the universe is supposedly infinite, but if I had a beam of light and it was really strong, and I project it in one direction, then eventually what's going to happen? You guys know? It's going to come from behind and keep going. Because we believe the universe is actually curved, and that's weird stuff. The simplest explanation, okay? You're somewhere on planet Earth on the equator, and you want to fly to somewhere else on planet Earth on the equator. So you just fly, over the equator, right?
No.
And that's the longest possible route, isn't it? Wait a minute. So if I'm looking at a map of the world, and you take 2 points on the equator, then the shortest distance between 2 points is not a line segment? No, definitely not. It's an arc. Because the globe is curved. So that's why if you're flying around the equator, you're actually going to probably go north a ways and come back down because it's shorter. That violates all reason, doesn't it? So the idea, I always say, think of a globe, right? So the shortest distance between 2 points is usually not a line segment. Because then when I translate it to a map, it's not going to be the line segment. That's why planes will fly north before they come back down. It's shorter. I know it violates reason, but that's literally the concept behind things like non-Euclidean geometry, which is probably not something you're going to run into unless you go off into the physics world or something, get really, really crazy. But the hyperbolic functions are trig functions of imaginary angles. It's kind of a scary thought, but the actual use of them is actually pretty simple. So where does it come up? Why in the world would we study these in the first place? Well, you're going to be an engineer, you really need to know about these things because they do come up. I'm going to give you the simplest example that I can possibly come up with. All right. If I draw the graph of the hyperbolic cosine using the exponential, right? E to the x looks like this. E to the negative x looks like this. So if I add those together and then take half, I'll get kind of an average, don't I? It'll kind of be, you agree it's probably more like that. This is called catenary. Am I spelling it right? It's called a catenary. It's kind of an important shape. I want to hang a cable across to the other side. I want the cable to be perfectly level. So I'm going to tighten it until it's perfectly level. Is that possible? No. Violates all laws of physics. Doesn't matter if it's made of the strongest substance, what vibranium and adamantium, and think of everything, in superhero land. No, it will snap before it gets straight. It's physically impossible because of one thing. Gravity. The shape that all hanging cables describe is a catenary. I'm going to put a solid metal beam 3 foot thick across the way. It's still going to have sag. Now, it might be at the molecular level, but it's still going to sag. It's impossible not to. It's absolutely impossible not to sag because of gravity. So we usually describe loosely the hanging cable. Okay? Did people figure this out a long time ago, how to deal with that sort of thing? When you have to do something over a great expanse?
Breaking it up?
The Romans figured this out. What did they do?
Oh, arches.
Arches, domes. Oh, because if I go flat across, I'm going to get dip and eventually structurally unsound. Now, how many have ever been to Vegas, for example? Hotel in Vegas. You're downstairs at the hotel and you have this great expanse. And I've been there for many times. I competed nationally and internationally in karate tournaments all throughout the 80s and 90s, even into the early 2000s. And they're always held at like the MGM Grand or some huge place, usually on the bottom floor. So there will be walls, but all the walls are partitions. They're all temporary walls. They can be moved. So I'm down on a floor that's literally probably 2/3 the size of a football field. Large building. No pillars. Think about this for a moment. You have a great expanse and a bunch of stories above you. Why isn't the upstairs becoming the downstairs at some point? I mean, think about this logically. Could you imagine you're going 200 feet across and there's nothing? Yeah, it's because things are built in such a way because we know structurally that if things are going to sag because of a catenary, this is why if you're an engineer, especially a structural engineer, you have to know this because if you don't take this into account, then everything you build is going to fall down, quite literally. So, like I said, the Romans, the concept of an arch, right? So these buildings will have that in the structure of the floors. They'll have ways of doing this, and the things will all meet in the middle. They'll do things. It's brilliant design, okay? But it wasn't always that way. Have some fun for you. How many are familiar with the band REM? Yeah, one of my all-time favorites. They've been around since a million years. One of their biggest hits, 1985, a song called Fall on Me. Everyone thought it was a love song. Watch the video. There was a problem in the United States. We actually there were buildings that were literally falling down, gigantic structures that were falling down and collapsing and caving in, and a lot of deaths. In the 70s, buildings were burning down because they didn't put in proper sprinkler systems, and they made disaster movies back then, Towering Inferno and places like you're on the 100th floor and your building's on fire and none of the elevators work and that kind of stuff. But the problem is that in this video they're showing us there was a problem in the United States that we were building things badly, always the lowest bidder kind of stuff. And people were not taking into account structural things like this, the integrity. And so buildings were collapsing because of just simply the gravity. The weight of the building would cause the building itself to collapse and, people were killed. And so the entire way big buildings were built was completely changed and revamped. So this is not what a hanging cable looks like. Well, this would be with either the X. What if it's either the 1/10th X or either the 1/100th X or 1/1000th X? You see how I'm flattening it out? Okay, so if I understand there's always a dip, I can control how much. If I know the equation, then I know how to work with it. But the thing is, I want to go across. Well, I'm going to use dental floss, right? Because that's not very heavy. Well, it's also structurally probably not very sound. So when I'm pulling, it's probably going to snap sooner. So the thing is, it's not possible to have a hanging cable ever be flat. So even the beam, in a sense, is a hanging cable. It's just going to have a lot less dip in it. So if you understand, if you're an engineer, you have to understand these if you're going to design something. So all we're doing is talking about the mathematics. Now the graph of the hyperbolic sign it's uglier. That doesn't have the physical meaning like this one does. So there is one exception. Generally speaking, when you're taking the derivative of a hyperbolic function, you just leave it as a hyperbolic function, because the answer to this is just going to be a version of this. The exception is if your argument is a natural log. This is the only time there's an exception. So let's suppose y is equal to the hyperbolic cosine of the log x. Then dy dx would be the hyperbolic sine of the log of x times 1 over x, or be more useful to write like this, okay? Everything I said is true, everything I said is correct, but that answer can be greatly simplified, hugely simplified. If your argument is the natural log and nothing else, then by changing this to the exponential version, you notice something? Oh, what's e to the log x? I haven't taken a derivative, this is just the function. What's e to the log x?
E to the log x.
Log
X.
This is x.
log base
E to the log base e of x is just x. Oh, so what's this guy? Well, that's a -1, so bring that up as an exponent. If your argument is the natural log, this is the one time that you're actually going to put it in the exponential form and evaluate it. The hyperbolic cosine of the natural log function is just this. So then the derivative is what? Which doesn't look very scary. That looks pretty harmless, doesn't it? Again, only if the argument involves natural log would you do this. Every other time, you just leave it like that. So far, so good? There aren't a lot of identities involving the hyperbolics, but there are a handful. Actually, I'm going to make this, I'm going to make this hyperbolic sign. Sorry. I've been doing way too much with hyperbolic cosine. It's getting way too much play here. All right, I want the derivative. Actually, let me go one second. Sorry. Simple tangent. One distance. In fact, let's go one step further. Let's make it an inverse tangent. Oh, now it's fun. Okay. It doesn't matter what function I have. I'm doing the derivative of the function and then the chain rule factor. Should I change this to the exponential version, do you think? No, there's no advantage. It's just going to be really big and really ugly. All right. So the derivative of the inverse tan, do you remember? I'll do my part. Quotient. What's on top?
N squared.
Inverse tan. Getting your way back machine, I think it's all the way back to Monday of last week. What's this? You remember?
1 over 1 plus x log.
Oh, okay, so what's this going to do? Hyperbolic sine squared. Is there a chain rule factor? Times what?
Times 2x.
You're thinking way too much. What's the chain rule factor?
Hyperbolic cosine.
Hyperbolic cosine. Can I just go ahead and put that on top?
Mhm.
Yeah, save myself a step. All right, I'm good, right? I can't go any further, can I? I'm winking at you. My left eye, so you know something's up. Left eye winks always means something's up. I can't go any further, right? Wait a minute, didn't we just come up with a Pythagorean identity for the hyperbolics? What did it look like again? Do you remember? Wasn't it the square of the hyperbolic cosine minus the square of the hyperbolic sine equals 1?
Oh. That's just hyperbolic cosine. Square.
So that's, oh, that's cool, huh? Can I reduce this further?
Mm-hmm.
To what?
Hyperbolic cosine.
Can I go further still? What's the reciprocal of cosine?
Secant.
So what's the reciprocal of the hyperbolic cosine?
Hyperbolic
Secant.
Yeah, I knew to write it. Sech. Whoa, so the derivative of this after all that was just this. If I stopped here, I'm not wrong, but I'm quite a ways from the finish line, aren't I? This is one of the rare times that there's an identity that you can employ here. And that Pythagorean identity, again, it's not going to show up very often, but occasionally it might show up. The square of the hyperbolic cosine minus the square of the hyperbolic sine equals 1. That's called sometimes the Pythagorean hyperbolic or hyperbolic Pythagorean relationship. Okay, they gave me that. So, derivatives of the hyperbolic functions are just like derivatives of anything else. You have some very basic rules, particularly hyperbolic sine and cosine, but there's no negative in these derivatives, is there? So the derivative of the hyperbolic sine is the hyperbolic cosine, but the derivative of hyperbolic cosine is the positive hyperbolic sine, okay? Because the I thing that was going on earlier, okay? Any questions so far? Be okay with that? I think we're probably in a good place here. Okay, so we're going to stop that.